Hi everyone, my name is Charik Yang. Today I am presenting self-supervised video object segmentation by motion grouping. This work is in collaboration with Hela Lamdour, Erica Liu, Andrew Zisserman, and Weili Xie at VGG, University of Oxford. Over the past years, we have seen so much progress in object segmentation. Current systems work great and are capable of segmenting things from cars to humans with good accuracy. Even so, training a segmentation model this way requires a lot of manual annotations, with each label frame taking up to an hour. Labeling thousands, if not tens of thousands, of these is simply not scalable. Moreover, in the natural world, there exist cases where relying on appearance alone is not enough, such as segmenting camouflage animals. Therefore, in this paper, we aim to solve both problems by doing segmentation using motions in a self-supervised manner, which means without using any manual annotations. To achieve this, we adopt an autoencoder framework, which decomposes the input optical flow into layers. Each layer contains an optical flow and an alpha channel. Intuitively, the reason why this layered representation works is that the foreground movement, which is caused by the subject in the video, is independent to the background, which is caused by the camera motion. The alpha channels end up as the segmentation mask after training. To train this model in a self-supervised manner, we reconstruct the input optical flow by linear composition of the layers using the alpha channels. We then simply train the model using a pixel-wise regression loss. The architecture of this model consists of three parts. First, the encoder, which encodes the input optical flow into a feature map. Next, the iterative binding module, which groups pixels of similar motion together with a transformer variant called slot attention. More details about slot attention can be found in a reference paper, but in a sense, it is performing a similar role to a soft k-means clustering using transformers. This is done by having multiple query vectors and a softmax applied along the query axis, which forces the query vectors to compete to explain part of the input. After iterative refinement, each pixel is then assigned to one of the queries. Lastly, the decoder, which decodes each query vector into a full resolution mask and optical flow. This involves a broadcasting operation, followed by a series of transpose convolutions. One of the challenges in this framework is that when the object undergoes similar motion to the camera, as shown in the figure below, it violates our independent motion assumption. Hence, the object will not be clearly visible in the flow field. To overcome this problem, we compute flows with different frame gaps, both positive and negative in time, and force consistency on the inferred alpha channels. This consistency comes in the form of a pixel-wise regression loss between the masks. Note that layers are commutative, so the loss is permutation invariant. The full architecture is shown in the figure below. We evaluate our model against four different datasets: SegTrack V2, FBMS 59, Davis 2016, and Moving Camouflage Animals, or MoCA. On the Davis 2016 video object segmentation benchmark, we show that the gap between self-supervised and supervised approaches has been largely minimized. Our model is also at least an order of magnitude faster than previous works at over 80 frames per second, as we do not use any post-processing in our model. On the MoCA dataset, what we can observe is that supervised methods that solely rely on appearance, such as COSNET, can perform among the top methods on Davis, but struggle to perform in MoCA. Our method, on the other hand, is competitive with the top supervised approaches that use both RGB and flow information, highlighting the importance of motion cues. Here are some qualitative results on the Davis 2016 dataset. Note that RGB is not used in our model and is only provided for illustration. Here are more results from the MoCA dataset. In this slide, we show some cases where our model fails, as our model only takes optical flow as input. If it is not informative, it will fail. Lastly, we think that there are a few potential directions to develop this work. We can generalize the model towards multiple objects with more layers, and we can also employ some heuristics, such as temporal smoothness, into the model. Thank you for listening. The full paper and code is provided on the website